Today, we are diving into one of the most fundamental and, frankly, coolest concepts in all of modern AI. It's the secret sauce that lets machines understand not just words, but the meaning behind them. We're talking about embeddings, and we are going to pull back the curtain on how AI actually learns to think.
So have you ever just stopped and wondered about that? You talk to a chatbot and it just gets you. It somehow knows that king is related to queen, but king and, banana are miles apart. I mean, how? A computer just sees ones and zeros, right? So how on earth is that possible? The answer is one word: embeddings. This is the magic trick. This is the core idea that lets us translate our messy, nuanced human world of language into the clean, structured, mathematical world that computers live in.
Okay, so here's our game plan. We're going to break it all down. First, we'll nail down what embeddings actually are. Then, we'll build this amazing mental model I like to call the map of meaning. We'll see how AI measures closeness, look at where this tech is hiding in plain sight in your everyday life, and finally, we'll get into some practical advice for all you builders out there.
All right, let's get right into it. Section 1. Let's get a really solid definition. What are we actually talking about when we say the word embedding?
So, at its heart, an embedding is basically a translator. It's a process that takes something we understand, like a word or a whole sentence, and turns it into something a computer can work with, a big list of numbers. Now, this list has a special name. It's called a vector. But, and this is the absolute key, it's not just a random jumble of numbers. This vector is specifically engineered to capture the semantic meaning, the vibe, the context, the very soul of the original text.
Okay, so we're turning words into numbers. Big deal, right? Well, the point isn't really the numbers themselves. The point is what those numbers allow us to create. And what they create is quite literally a map of meaning. The fundamental principle is just this simple. Think of every single vector as a coordinate, a point on a gigantic, multi-dimensional map. And on this map, things with similar meanings are placed close together. So the vector for dog will be right next to the one for puppy, and not too far from pet. But it's going to be on the other side of the universe from concepts like car or galaxy. It's a spatial representation of concepts. It's incredible. So how do we make this map? It's actually a pretty straightforward 3-step process. First, you start with your text. Could be a single word, a sentence, or even a whole book. Step 2, you feed that text into a pre-trained AI embedding model. The model does its thing, analyzing the context based on all the data it's learned from. And then, step 3, it spits out the vector, that unique list of numbers, that special coordinate on our map of meaning. Okay, so we've got this amazing map where similar ideas are all neighbors. That's cool. But how do we actually, measure the distance between 2 points on that map? How does the AI calculate that king is closer to queen than it is to banana? Well, the tool for this job has a bit of a fancy name, cosine similarity. But don't let the mathy name scare you. The idea is actually really simple. Instead of measuring the straight line distance, it measures the angle between 2 vectors. So if 2 vectors are pointing in basically the same direction, like puppy and dog, the angle between them is tiny, which means they're super related. If they point in different directions, the angle is thing. Simple as that. And that's exactly what's happening with our original question. The vectors for king and queen are pointing in very, very similar directions in this conceptual space, so they get a high similarity score. Meanwhile, the vectors for king and banana, they're pointing in completely different directions. The angle is huge, the score is low, and that is how the AI knows they have nothing to do with each other. Now, I know this can all feel a little abstract, but I promise you, you are using this technology all day, every day. So let's talk about where these embeddings are actually being put to work in the real world. Okay, first up, semantic search. This is when you search for an idea instead of just exact keywords. When you type in something like, what were those action movies from the 90s with the funny one-liners? The search engine uses embeddings to find things that mean what you're asking for. Then you've got recommendation engines. When your favorite streaming service suggests a new show, it's because the embedding for that show is super close to the embeddings of other shows you've loved. And finally, there's data clustering, things like automatically grouping news articles about the same story, all without a human having to read and tag a single one. All right, now, for all of you out there who are actually building things with AI, this next part is for you. How do you take these incredible tools and use them effectively?
So, probably the first and most important question you're going to have to answer is which embedding model you should use. You don't build these things from scratch, you use powerful models that have already been trained. But, and this is a big but, they are not all the same. You've basically got a key choice. For most general text, a general purpose model is going to work great. But if you're working in a really specialized field like medicine or law, you absolutely need a domain-specific model. It's been trained on that specific language, that jargon, so it's going to give you a way more accurate map of meaning for your specific world. It really is about picking the right tool for your specific job.
Using embeddings isn't without its challenges, though. First, there's something called index drift. Language evolves, right? The embedding for the word cloud means something completely different today than it did in 1980. That means you have to periodically update all your vectors, which is a process called re-embedding. And then there's a really important one, privacy. Because these vectors capture such subtle meaning, they can sometimes encode personal information without you realizing it. So you have to be incredibly careful about how you handle them.
So why does all this matter so much? Because good embeddings are the absolute bedrock for some of the most powerful AI systems we have today, like RAG. Imagine you have a chatbot that can answer questions about your company's private documents. The first thing it does is use embeddings to search and retrieve the most relevant snippets of text from those documents. It's using that map to find the right spot. Then, and only then, does it use that retrieved information to generate a smart, accurate answer. That two-step dance is called Retrieval Augmented Generation, or RAG, and it completely falls apart if your embeddings, your map, can't find the right information in the first place. And that really brings us back to our main idea here. At the end of the day, an AI is only as good as its understanding of the world. And that understanding is literally built on this map of meaning. A detailed, an accurate, and up-to-date map made from high-quality embeddings is what allows an AI to navigate the crazy world of human ideas with what feels like magic. And that leaves us with one last, kind of mind-bending thought. We started this journey by talking about mapping words and sentences, but these exact same techniques, they can be used for images, for sounds, for pretty much any kind of data. So if we can create a map for the meaning of a word, what else can we map? What's next? Complex scientific ideas, human emotions? The possibilities here are just starting to open up. Thanks for watching.